A-level physics, UGPE, paper 2, June 2021, 120 minutes, 2 hours, 90 marks. Question 1, multiple choice question. Which statement is not correct for ultrasound and X-rays? Ultrasound waves are longitudinal, X-rays are transverse. Let's have a look at each option. Both transfer energy, that's correct. So we're looking for not correct. Both can be diffracted. So all waves can be diffracted. So wave properties are they can reflect, refract, and diffract. So both are waves, regardless of longitudinal or transverse. Both can be diffracted. Both can be refracted. So as I just said, all waves can be diffracted, refracted, and reflected. As we know that ultrasound is a mechanical wave, longitudinal, and X-rays are transverse. So this is incorrect. Question 2. What cannot be used as a unit for Young's modulus? Okay, so let's have a look at what Young's modulus is. Young's modulus is the stress, so let's just write that down. It is the stress over the strain. Okay, so that's the stress over the strain, and what we have here is the strain does not have any unit. Okay, because strain is the extension over the length, and they both carry the same unit, so these units cancel out and end up with no unit. So therefore the Young's modulus has the same unit as stress. So stress is force over area, so that is pascals, so that there is correct. Force is newtons divided by meter squared, which is area. So Newton per meter squared. That is one way of looking at it. So Newton per meter squared, that's there as well. So we've got to look between these two. So what we're going to do is expand newtons into its base units. Now we know that newtons is force, which is mass times acceleration. So mass kg, acceleration meters per second squared. So kilograms meters per second squared, that is the Newton part, multiplied by per meter squared, and we get the m to the power of 1, that's to the power of 1, and then that's m to the power of minus 2. Those add up when we multiply, and we get power of minus 1 on the meters. So therefore the the stress is kilograms meters to the minus 1, seconds to the minus 2 in base units. So that there is the correct representation of stress, hence so therefore that's also the Young's modulus. So that leaves this one as being the unit that is not the Young's modulus, cannot be used for the unit for Young's modulus. Question 3. So we've got a wave and it is at a specific point in time. This axis is distance and it's centimeters. That's the height of that wave at a particular instant. So peak to peak, considering its distance, it's the wavelength. So if we look from 0 to 4 is from peak to peak. So 4 centimeters is the wavelength. We know that the speed is 20 centimeters per second. Okay, so he asks for what's the time period. So time period is 1 over the frequency, but we don't have the frequency. We have the speed, and we can look at the graph and see the wavelength. So therefore we'll use the wave speed formula. Wave speed equals frequency times wavelength. Rearrange that, find the frequency. So it's the wave speed, which is 20 centimeters per second divided by 4 centimeters. Now we don't need to convert into meters because the centimeters and centimeters cancel out. That would happen with the meters, and you'll end up with seconds to the minus one. So we know frequency is in hertz when the unit is seconds to the minus one, so it's 5 hertz. If you converted this into meters per second and this into meters as well, you would still end up with the number 5 here. Okay, and that's 5 seconds to the minus one, so 5 hertz. That's not what the question's asking. So if you found that, that is frequency, but the question is what is the time period? So the time period is 1 over the frequency, 1 over 5, which is 0.2 seconds. So that's the this is the trick with the examiners try to pull to get you to see this and this as a possible answer. So knowing the difference between frequency and time period is important. Okay, question 4. This question here, which quantity will not affect the viscous drag on a ball bearing? Now, here, ball bearing, small sphere, we know from EdXL that EdXL syllabus that Stokes' law applies for small spheres. So there's your formula that links the drag to the viscosity, the radius of the sphere, and this terminal velocity. So this is the terminal velocity that a sphere is moving at, and that will be the drag force when the sphere is falling at terminal velocity. Okay, so if we have a look at the variables here in Stokes' law, we've got terminal velocity, the radius, and the viscosity. So let's have a look. So this is the viscosity of the the fluid, the oil in which the ball is going through. So this will affect it, as we can see in this equation. Velocity of the ball bearing, clearly velocity is a factor that will affect the drag force. So that's a factor. The diameter of the ball bearing, that's directly linked to radius, so that also affects it. So these three can be discounted straight away. There's no density in here, so therefore is um, drag is not within this within Stokes' law. You also can look at drag. There's another formula in general. Drag is proportional to the density of the fluid times by the cross-sectional area of the object that is falling through the fluid and the speed of the object falling through the fluid. So this is a general drag equation. Now, as we can see, there is density there, but that is the density of the fluid that the object is moving through, not the density of the object. So if you were thinking and looking at a formula looking very similar to this, that density is not this density here. That's the density of the object that's moving through the fluid. This is the density of the fluid. Question 5. Two radio transmitters emit waves at a frequency of 1.4 megahertz. So key to think before even we look at the rest of the question, mega, that you need to multiply by 10 to the minus 10 to, 10 to the power of 6 to get that into hertz. So stationary wave is set up between two transmitters due to the superposition of radio waves. So what we need to know is this question is about stationary wave. So bring everything you know to the table about stationary waves. Now, so there is stationary waves, and it's to do with two radio waves interfering and producing a stationary wave. So the minimum distance between the two nodes, and this phrase from your notes, the distance from two nodes is always the minimum distance between two consecutive nodes is always half a wavelength. So from one node to the next adjacent node, the distance is always half a wavelength. Okay, so that's something to bear in mind when we're answering this question. So what is the minimum distance between the two nodes? Okay, so if we find the wavelength and then half it, we find the distance. So how do we find the wavelength? Using the wave speed formula. We just rearranged it to get the wave speed divided by the frequency. It's a radio wave, so the wave speed is the same as the speed of light, 3 times 10 to the 8. And the frequency is given to us as 1.4 times 10 to the 6, and we get 214 meters. Now you can see clearly 214 meters is there. However, you took that wrong answer because we are looking at the minimum distance between two nodes, and the distance between nodes is half a wavelength. So we have to half that value, and there you go, that value is there as well. So read the question very carefully. Okay. So the answer to this question is 107 meters. Question 6. So this is a question that crops up on many areas, where you change one thing, how does it affect another thing? So here we got three things changing: the cross-sectional area, the length, and the Young's modulus of a material. Okay, so which combination of the properties produce the smallest extension of the wire when the same tensile force is applied to the wire? Okay, so we're looking at extension, and the variables are force, cross-sectional area, length, and Young's modulus. So let's try to get them all together in one formula. So we know the Young's modulus is stress over strain, which is the stress is the force, tensile force over the cross-sectional area, and the strain is the extension over the original length. So that is the Young's modulus. I'm just going to make that look nicer and then rearrange that so that we get the force times the length divided by the cross-sectional area times by the extension. So that's the Young's modulus. However, it says what's the effect on the extension. So what I need to do is just rearrange this to get extension equals. So we've got extension equals the tensile force times by the original length divided by the Young's modulus and the cross-sectional area. So in this question, we have got that we have the same tensile force each time. So we can seemingly ignore that throughout because that's not affected every single time. So the three variables which are changing are cross-sectional area, which is there, the length, which is there, and the Young's modulus, which is there. So let's have a look at A to deduce which one has the smallest extension. Okay, so where are we going to see that? So the original, that's what we start off with. F is the force that we'll just say it's a tensile force. They haven't used a letter for saying this, so we use the general term F. L is what they use for the length, so I'm going to put L in as the original length. E is what they use for Young's modulus, so I'm going to use the E as I've done before, so that's fine. And rather than use L here as the cross-section areas A, they've used X. So I'm going to use that as the original cross-section area. So that's what we start off with. That's just the same formula here written using the letters that they have got here. So first one, we've got the same force. We've got 3 times the length. So rather than L, we have 3L divided by the Young's modulus. So they've used E. So I'm going to use E and X as the cross-section area. So there we go. We've got, that's the first expression. Now we pull the number to the front. So that's 3 times FL over EX. So the original was that, and it's 3 times the original. So that's 3 times the original extension. Next, let's look at, that's the same force as before. Okay, L is, so we're looking at B. L is the length of the wire. E is the Young's modulus. And now the cross-sectional area is twice the original. So I'll put 2 times the original there. And if I move that number to the front here, that is a half. It's at the bottom of the fraction. So it's a half the original extension. The next one, C. Same tensile force times by 3 times the length, because the length here is 3 times the original length. So I put 3L in the position of L, and it's 4 times the Young's modulus. So in the position of E, I've put 4 times the Young's modulus, and the extension, the cross-sectional area remains the same. So I've put X there, and those numbers come out to the front here. So it's 3/4 of the original. Okay, and then D, finally, F is the same tensile force. L is the length, hasn't changed, stays as L, so I'm going to still write L, but the Young's modulus is 4 times larger, so I'm going to write 4 times the Young's modulus, 4 times that there, and the cross-sectional area is twice, so rather than write X, I'm going to write 2 times X, and that at the bottom, that's 4, and that's times 2, so that's 8, and I move that out to the front, and that's 1/8 of the original. That's the original, and we can see there's the original. And we could actually write X here, X here, X here, because we know that is equal to X. But I've just left it there. So we can see clearly that that's 3 times the original extension, half times the original extension, 3/4 times the original extension, and then 1/8 times the original extension. So that there is the smallest, an eighth of whatever we had at the beginning is much smaller than all of this there. So question 7, a progressive wave, frequency 150 hertz, travels along a stretched string or speed of 30 meters per second. So we got frequency, we've got a speed, and we know that with frequency and speed, we can work out wavelength. Okay, now that there is the wavelength. So the wavelength is 30, which is 30 meters per second, divided by 150 hertz, 150. So that's the wavelength is 0.2 meters. So that's something that straight away you're like probably thinking, okay, that's something I can work out with speed and frequency. So let's just work it out there. It is going to be important, whereas because we're trying to find out the phase difference between 2 points that are this distance apart. Okay, so we know that the phase difference phi is equal to the path difference over the wavelength. So the fraction that this is compared to the wavelength times by 360, and that will give us the phase difference between those 2 points. Okay, so that there is the path difference, the distance between 2 points, 50 millimeters. Because that's in meters there, I'm going to put this into meters as well. That's actually 0.05 meters. So that there is 0.05 meters divided by the wavelength times by 360. And these 2 points are 90 degrees out of phase. So these 2 points, which are this distance apart, are 90 degrees out of phase. So therefore, we've got that there. Okay, so question 8. Which row shows a change in velocity, frequency, or wavelength of an electromagnetic wave as it travels from optically less dense to optically more dense? So we're going from less dense to dense. So we know that the speed decreases. So it's that or that. So when light goes from less dense to dense, speed decreases. So it's either A or C. We know that the frequency remains unchanged. So therefore, the answer now is most likely C. And we know that the wavelength decreases as well. So this is what happens when light goes from less dense to more dense. The velocity decreases, the frequency of light entering the medium remains unchanged, and the wavelength decreases as well. So here, if we write down V equals F times by the wavelength. We know this is a constant, so if the speed decreases, this will also decrease. But something to remember, that the frequency of light, when it enters from one medium to another, remains unchanged. Question 9. Okay, so a load of 50 newtons is suspended from a wire that has a cross-sectional area of 1 millimeter squared, and the stress in the wire is in pascals, is between something and something. So here what we've got is Pascal as in stress, though that's force over area. So 50 over the cross-sectional area. Now we cannot you work with millimeters squared here. Okay, so let's have a look at converting millimeters squared into standard units, because to get the stress in pascals, you must have newtons and meters squared here. So 1 millimeter meter squared, so 1 meter by 1 meter, we're not looking at a cube, so let me just rub that out there. Okay, so 1 meter by 1 meter. Okay, we know that in 1 meter we got 1000 millimeters, in 1 meter we got 1000 millimeters. So 1 meter square, okay, is equal to 1000 millimeters times by 1000 millimeters, okay, which ends up being 1 times 10 to the 6 millimeters squared. So in 1 meter squared, there are 1 million millimeters squares. So 1 million little millimeter squares are in 1 meter square. Okay, so if we wanted to convert from millimeter squared to meter squared, we multiply by 10 to the minus 6 or divide by a million. Okay, so if we wanted to go from millimeters to meters, so from 1 million to 1, that you'd have to divide by a million. So there'll be 50 divided by a million. So you can 1 times 10 to the minus 6, that's going to give you an answer. I don't even need to do this calculation. Something in between a 10 to the power of 6 and 10 to the power of 9. You can do this calculation and you'll actually see the answer will fall within these two powers. Okay, from just looking at that, I can just see that that's the same as multiply by a million. Okay, so that'll be 50 million. So 5 times 10 to the 7, that's 10 to the 7. None of those falls below 10 to the 6, and it's not above 10 to the 9 either. And question 10, which gives the regions of the electromagnetic spectrum in the order of increasing wavelength. Okay, so we know that radio waves have the largest wavelength, and we know that gamma rays have the smallest wavelength, gamma rays and X-rays. So increasing wavelength. So starting off with the smallest, ending with the largest wavelength. So we know that X-rays or have small wavelength. We know UV will follow that. We then know visible light will. Then after that will be infrared radiation. Then it will be microwaves, and then it will be radio waves. Okay, so what we've got, this kind of follows the pattern. This is incorrect because microwaves should be way beyond, right at the end. This is the, well, this is all mixed up. X-rays should be on this side, infrared should be on that side, radio waves should be at the end. So that there is not increasing wavelength, it's all a mixture. Microwaves, infrared, UV, X-rays, that's the complete opposite. That is decreasing wavelength. Okay, so this here is the complete opposite. That will be increasing frequency, okay, and decreasing wavelength. This is increasing wavelength and decreasing frequency.